Welcome to Get Out of a Bind with UNIX Sockets, a Linux Fest Northwest exclusive. Today we'll be looking at implementing a transparent reverse proxy for HTTP or HTTPS servers, although the same technology can be used for any protocol. Now, as this is a presentation intended for anyone from Linux newbies to veteran system administrators and programmers, we'll be starting by looking over some basic terminology. Starting with files. Now, everybody knows what a file is, a way to store data on a computer, but it's used for far more than that, and the terminology can get a little bit complicated. Specifically, what's a file handle versus a file descriptor versus a file description? It's not really that difficult. A file handle's kind of the shorthand we use for the view a programmer gets. In Python, things like sys.standardin, or when you open a file, what you're dealing with there is a file handle. Behind the scenes, all file handles are associated with a number, just an integer, 0, 1, 2. That actually points to a table in kernel space that maps those numbers to the actual file description table. And here's the important point. Multiple file handles, multiple file descriptors, can point at the same actual file description in kernel space that points at some real resource. And the second important point here is that in UNIX sockets, whether UNIX sockets or TCP sockets, are file handles as well. UNIX sockets actually have some additional features. Send message, a system call, can be used to send one file descriptor from one process, in this case PID1, could send a file descriptor through a UNIX socket to a second process, PID2, and it would actually then point at the same file description in kernel space, which would let the first program close that file descriptor and leave the second program to do whatever it wants with it. Now, client's simple enough. It's the side of a socket that starts a connection. Pretty straightforward. Servers, the side of the connection that creates a socket and sits there waiting for a connection to come in. Of course, a single program can act as both a client and a server, and that's where the terminology gets a little more difficult. We'll come back to that later. Now, we're trying to implement an HTTP proxy, but what is a proxy? Well, a proxy just lets you pass traffic. It sits in between a client and a server, and it relays traffic back and forth. Usually when you mean a proxy, it's something that acts on behalf of a client. And that leads us to the next term, which is a reverse proxy, which is also just a proxy, except that instead of being set up and acting on behalf of the client, it acts on behalf of the server, and it often allows both multiple clients and multiple servers. Which, again, we'll come back to how this relates later. Alright, so what problems are we trying to solve here? Why do you need a reverse proxy? Well, the first challenge is efficient CPU utilization. And that's because modern computers have been getting faster, but not as much as we might like. Primarily, new computers just add more cores, which let them do multiple things at once, but not really any faster for any particular task. So,
if you have something like a web server, and you want to make it more efficient, you have to come up with a way to split the incoming connections out so that each one goes to its own CPU core, and the CPU cores can then be more fully utilized at any given time. A reverse proxy is a simple means to do that on one physical machine. Note that reverse proxies can also be used for load balancing between multiple physical machines, but that's not something we're going to go over today.
Second use of reverse proxies is for virtual hosting, where you run multiple virtual websites off of a single IP address and usually a single physical box. This is fairly common with cloud providers when you use what's called shared hosting, where you actually have multiple different websites hosted on the same machine. You need a way to figure out what website they're actually trying to reach, and the system that's used for that is that the browser actually specifies the host name. Typically, it's the host name that you put in the address bar. Of course, this presents some unique challenges. Primarily that for the reverse proxy for the web server that's using virtual hosting, to tell which website the user is requesting, it has to start reading from the socket, start reading from the incoming connection. And if you're trying to use SSL, it gets even more complicated because, well, the requested host name is available in the initial TLS header that gets sent. You still have to read from the socket to get that information, and typically this means that reverse proxies can't use end-to-end encryption. The encryption's actually done on the reverse proxy, which has some drawbacks. For one thing, all of the TLS certificates have to be available to the same process. Now, you could get encryption through the reverse proxy anyway using the Start TLS extension for HTTP, except nobody supports it, and in fact it's being deprecated and going away. So, given that that's the problem we're trying to solve, what do we have for solutions? Well, the standard solutions for efficient CPU utilization, the old solution, and this is something that the old Apache web server would do, is called forking, where you just create a second copy of the web server with each connection that's coming in. It's very simple from a programmer's perspective, but it has some severe resource limitations. The first is that it requires starting a new process for every client, which takes a lot of memory comparatively, and it doesn't easily let you preserve the runtime state because it can't keep running because it has to start a new process for every incoming connection. Second solution is some sort of load balancer. Now, the standard approach to this was actually added in 2013. It existed in BSD land before that, but Google got it included in the Linux kernel in 2013, where you pass a flag when you open the socket to the Linux kernel to say, hey, let other programs listen on the same IP and port combination. The kernel then just hands incoming connections one after another through to the waiting clients. And that works reasonably well. There's two major drawbacks. The first is that it doesn't work well in conjunction with named virtual hosting. Or rather, you can't dedicate one process per virtual host, or multiple processes per virtual host. And the second problem is that there's no way for a client process to flag the kernel to that it's ready for more work. In theory, you could listen. The listen system call is used to tell the kernel, hey, I can handle up to X number of waiting connections. If you set the number too high, then you don't efficiently distribute work between the various threads, and if you set the number too low, then you'll end up bouncing connections, refusing connections, because nobody's available to handle the work. The ideal solution would have the incoming connection sit in a queue until a worker thread is specifically ready for them, and then pass them along. Now, there is one additional system mentioned here, and that's using a worker pool, where instead of restarting the program every time and having to allocate stack for each client, you create a list of worker clients and you pass them incoming connections one at a time, typically from within a single process space, which makes passing the incoming connections easy. This is the approach that things like Nginx do. And that works reasonably well if everything you want is all running within a single process space. It doesn't work nearly so well if you have multiple different programs that all need to be able to serve HTTP content over the same connection. Now, standard solution for virtual hosting. There's actually already a proxy protocol. Sometimes you'll see it called a transparent reverse proxy because the client library on the other end tries to recreate the information that's lost. Basic idea here is that when data comes in, it gets relayed to the provider upstream, including information like what was the actual IP address and port number that the connection originated from. It's not really transparent, though. The application code on the other side has to be aware of it. There's some other limitations performance-wise. For one, you can't use send file, which is a way to send data out from a file out network connection or similar without having to copy it through userspace. And that's because you can't call send file from a socket to a socket. And so that means that you end up needing to copy the data to userspace and then back from userspace. And the additional system calls require extra context switches. Also, because you have to pass the client IP address and port number before you actually start relaying the real data, it makes it difficult to implement end-to-end encryption from the upstream server through to the client. Second option is to use multiple IP addresses. You can just create a second virtual network interface, give it its own unique IP address, and then have your DNS server pass out the individual IP addresses depending on what host name was used for the lookup. And while this lets you use the same physical box, IP addresses, are, especially IPv4, are in something of short supply, so it's not really a solution to the underlying challenge. So here's a better solution, and it's an actual transparent proxy. The goal is that the downstream program can't even tell that it's behind a proxy, and there's some success with that. It's a little bit easier if you can modify the downstream program a little bit, but we'll discuss that when we get to the limitations. In reverse order here, for virtual hosting, the idea is that once you pass the client connection through to the upstream server, it's as though the connection were made directly without the reverse proxy in the way. Which means that other than accepting the file handle for the handoff, there's no additional requirements for the upstream server to speak a different protocol. If it wants to directly ask what's the peer address or peer port, it can do that. If it dynamically queries what's the protocol used, it'll correctly respond IPv4 or IPv6 or whatever protocol you're listening on. Using it for load balancing. The primary advantage is that the decision for which upstream server accepts the connection is made in user space, which means that the upstream servers can actually explicitly signal when they're done and ready for more work, or they could signal if there's a long request that they expect will take them offline for a while. If a server has to shut down due to an error or similar, it can actually signal back to the central user space program that it's got a problem and pass the file handles back so that the connections don't get dropped. Also, if you need to upgrade services, You could register the new program before deregistering the old one, and once again have a zero downtime, no dropped connections upgrade path. Alright, so this sounds wonderful. How does it actually work? So, little bit of nomenclature again. Your clients are the machines out on the internet that are sending requests trying to connect to some host name. They go to the edge server, and that's just a convenient way to distinguish the edge server from upstream servers. Upstream servers are, of course, your actual websites, example.com, test.com, etc., all hosted off of the same physical box. So, what's the job of the edge server? Well, it's what actually listens on a TCP port. Port 80, port 443. You can actually have the same process listen on both, since it's pretty easy to sort out SSL versus not. If you don't want your edge server running as root, which, little hint, you shouldn't, it's pretty easy to use a setuid wrapper. Authbind's a good, easy to configure one to let it have root long enough to bind to the port, and then drop root for actually serving the connections. It then waits for clients to connect. When a client connects, it reads the first kilobyte of data. That's sufficient for a TLS connection to have the host name. It's sufficient for HTTP servers, for connections from Firefox or whatnot over HTTP, to read the host name from the host line. Message peak is a flag that you can use when you read from a socket that tells the kernel that you want the contents of the internal socket buffer without actually moving the pointer forward or discarding the contents of the socket. So that makes it appear from the upstream server's perspective like nobody's read from the client, from the socket so far. Then, after it has read the initial information from the socket and determined which host to send it to, it makes a connection to the upstream UNIX socket and passes the file handle over the socket using the send message system call. It then waits for the upstream server to close the connection. And the reason for this is that if the edge server accepted the connection, opened a connection to an upstream server, passed the file handle off, and then immediately closed the connection, closed the client, and moved on, the kernel would actually potentially see that as a signal that it's okay to clean up the underlying file description, and so then the upstream server would see a broken pipe when it receives the sent message. So just to avoid any potential issues that way, we wait for the upstream server to close the connection, and then the edge server can close its end of the connection. It also closes its copy of the client's file descriptor because it doesn't need it anymore. It's already upstream. Alright, so what do the upstream servers do? Well, they listen on a UNIX socket instead of a TCP socket. And instead of waiting for a connection from the client, they wait for a connection from the edge server. Once they get that connection from the edge server, they call receive message on it with some additional flags to ask for any file handles that are being passed over. They then register the connection however they need to and close the edge server connection. Now, what do you do when you have a program you don't have the source code to, or you don't really want to take the time to modify, or most commonly, you don't want to have to keep modifying every time a new version comes out. That's where the upstream shim comes in. It's just a small LD preload library. It's like 100 lines of code or so. And it intercepts, redefines the socket bind and accept system calls. Importantly, it reroutes them so that when a server, light HTTPD or similar, calls socket to create a new socket, instead of getting a TCP socket, it gets back a UNIX socket. And when it tries to bind it to a TCP port, instead of binding it to a TCP port, which obviously it can't do because it's a UNIX socket, not a TCP socket, it binds it to a UNIX socket on the file system. The path can either be set explicitly or can be deduced from the port that was requested. And then when it makes an accept system call, if it's trying to accept a connection on the socket that it previously used for the bind system call, instead of calling the underlying accept, it calls the underlying accept system call. When it gets the file handle back from that, it then calls receive message on that, and then closes it, and then returns the file descriptor that was passed through it. And all of this means that from the application's perspective, you can't tell that it's not listening on TCP. And I've tested it with Python and light HTTPD and Nginx. There are a few things that don't work, but we'll get to that. Some things notice, specifically, anything using ePoll or eSelect is likely to fail with this. And then there are a few programs, Netcat, SoCat, they actually check the type of socket that gets passed back to them from the socket system call, and they throw an error and die if it's not the type of socket that they're expecting. That's probably a good thing. Probably more programs should do that, but honestly, this kind of thing is not particularly common. So that's kind of the high-level overview of how it works. How well does it perform? Well, if you're interested in checking out the code, there's a link to my initial implementation of it in Python on GitHub. There's a C++ implementation in progress, and I hit 40,000 connections a second using a Ryzen 1700X. Now, that's not serving any real web page. It was just like about 2 kilobytes or so worth of static web page. But honestly, the point here is that your limitation is not going to be from the proxy itself. It's going to be from whatever web server is behind it. All right, so there is one potential drawback, and that's that you can get a CPU race if a client misbehaves. Specifically, if the client sends the start of a valid TLS or the header or the first line of an HTTP request, then the socket will be listed as ready to read. If the start of the TLS header doesn't include the server name indicator or the host line in the case of an HTTP request, then the edge server can't actually determine which upstream server to pass it to. And unfortunately, there's no way to ask the kernel to notify the edge server when additional data comes in, which means that the only way to resolve the issue is to just check and see if more data has been received by calling receive with the message peak flag on every server loop. There is theoretically, we could create an extension for the kernel for ePoll that would tell the kernel to notify again on the socket, but only after additional data has been received. But without that, the only option is to handle it in user space. There is, of course, fortunately, a workable solution. The simplest solution is to just drop the connection. Specifically, if the client begins talking, now the client can connect and not talk for as long as it wants without causing any problems. But once it starts talking, once the socket comes back from the kernel as ready for reading, if the TLS header isn't there, at least the first kilobyte of it, or if the host line isn't included within a second, that's probably a client that's not actually working, whether it's because there's a connection problem or because someone's trying to launch a denial of service attack. The odds are good that this is not going to turn into a connection we actually want, so it's safe to drop. You could also create a pool of these slow connections and give them a little bit more time. Just depends on what your particular use case is. Since we still have some time, here's some other considerations when comparing conventional HTTP proxies with a transparent reverse proxy. The first is the principle of least privilege. This is a general security advice for computers that programs or users should only have the permission to do what they need to do to accomplish their purpose and no more. And in the case of the transparent reverse proxy, the upstream servers don't need to listen on privileged ports. In fact, they don't need to listen on the network stack at all. This means that you can run the edge server as a user that has access to the network stack and can bind port 80 and port 443, but the actual heavy lifting programs that touch the database or whatever sensitive data you have don't have to actually connect to the network directly. And even if they don't have permission to connect to the network, they can still find out what the upstream IP address and all of that is. Second, as I implied with the previous answer, it works across users. This could be used to provide the old public HTML pages for multi-user systems, and related to the principle of least privilege, it means that you can have each different server service running on the system have its own user account, its own database, whatever, without actually having to have any files held in common. Related to that, you can pick which users can provide an upstream service, because you just have to restrict who has access to the directory where the edge server is going to go looking for the upstream sockets. And because it's UNIX sockets using the standard file system, you can use any of the standard file system permissions, including the set FACL access control system call to have very granular permissions. Now, building on the fact that you don't need network access and it can run with different users, you can actually use it across containers, Docker containers or whatever. Now, to do that, you just have to have a shared folder between the host and the upstream, between the edge server and the upstream server, and have the UNIX socket sit in that shared folder. And in fact, you can share the same folder between two different Docker containers, and they can pass file handles between them. All right. Now this is the last section we're going to go over, and it's kind of where I see going from here. My current implementation is pretty simple. It aims entirely for simplicity. The host name to the host name to socket map is static. You specify it on the command line when it starts up. It would be fairly easy to implement a dynamic registration system. For anything I do, it's not really needed, but if you were trying to scale this out to a more complicated system for server hosting or whatnot, it would be pretty easy to add and remove them. This is a major source of the inefficiency in the current implementation, and it's that the upstream connection gets closed on every request, which means that it has to be opened fresh on every request. There's no reason it has to be this way in general, other than for the shim library. The shim library needs to not dangle any open file handles, so it really has to close the connection with every request. And so the other client library was implemented to match. If you had control of the upstream servers and could have them handle the patching, the file handle passing explicitly, and I have patches for Nginx and a couple of other programs to do that, then there's no reason that you have to close the connection on each request. And if you didn't, then that opens the door for better queuing, where a upstream server can explicitly indicate how busy it is, or other similar sorts of messages passed back and forth. The C++ implementation that's in progress will have that version, that system implemented, but it's not quite ready for use yet. That brings us to the end of the presentation. If you have any questions, feel free to leave them in the comments down below or ask them on the Linux Fest Northwest forum. If there's interest, I may be available to do a live stream or something answering common questions or helping explain things that don't really fit into a question and answer format. If you're interested in the underlying technology, check out my GitHub repo for it, and thank you for your time.